And we start chapter 3. So like I said, this is going to be the abridged 3.1 notes. If you want to see all the notes regarding transformations of exponential functions, then you can watch the video titled section 3.1a notes that are on YouTube. It will go over this material here that I'm not going to do because it's legitimately just, can you plug in a number for x and evaluate, and then tell me transformations from this set of examples right here. We're not going to do any of that. Instead, we're going to jump right to the most important part of section 3.1, and that is exponential functions. You'll notice that the title of the notes is exponential and logistic functions, but logistic functions is the stuff that the state of Florida has removed. They're no longer standard, so we're not going to spend our time working on them. That's not to say they're not useful. That's just to mean that the powers that be right now don't think they are. Because we know that they all went to school and studied mathematics, right? Exactly. Okay, the parent exponential functions. These aren't new. These are things that you should have worked with a lot in Algebra 2. In Chapter 6, if you remember exponentials and logarithms, everybody's favorite material, right? Logarithms. Yay, logs. Nope. I'm a log magician. I love those things, and I will make you love them as well. Okay, but before we could talk about logarithms, we have to talk about exponentials. There are two basic exponential functions, the exponential growth function and the exponential decay function. I say basic because in order for us to call them growth and decay functions, technically they have to be above the x-axis. Now that's not to say that below the x-axis doesn't exist. Of course I could take either one of these and reflect them below. Of course I can. But then they're just called exponential functions. They're not called growth or decay. They're just called exponential functions. All exponential functions have a horizontal asymptote. My phone is going bananas right now. They all have a horizontal asymptote somewhere. They do not have a vertical asymptote. Yes, both of these graphs do get really steep really fast, but it is not approaching a vertical line. It's just going up really, really fast. Our textbook authors say that this is the parent exponential function. I'm going to respectfully disagree, and I'm going to include a couple more pieces of it. You should have a minus h in your exponent position and a plus k afterwards. And we have used the letters h and k before in our mathematics, specifically when we talked about parabolas. The letters h, comma, k are the coordinates of the vertex of a parabola. Exponential functions do not have a vertex. However, h and k still represent the same kind of things. They're the horizontal shifting and vertical shifting of the parent function. That's what the letters h and k represent for us. Why is it k? We use k for constant, and we don't use c for constant because c is used in other equations for other things, like in the standard form of a parabola, ax squared plus bx plus c. So the c is also used for constant often, but we use k and h for our vertex for parabolas and also to represent horizontal and vertical shifting, but it's really because of constant. I think, don't hold me to this, the word for constant in Latin begins with a K? It does? She's shaking her head yes. I've looked this up before because I was wondering the same thing, because it starts with a K in Latin. Okay. Other than the horizontal and vertical shifting, what else is going on here? The letters A and B. A is the same thing that A is in every other equation. It's literally just going to represent a vertical stretch or shrink. But B now stands for base. See how B is how you start the word base? B for base. What separates this chapter from our last chapter is now our exponent is the unknown. Our exponent is the variable. Whereas in last chapter, the base was unknown. X to the second, x to the fourth, x to the scary eighth. The base was unknown. Now we're going to know the base. It's going to be a number. The exponent is what's unknown. Speaking of the base, and I said it's going to be a number that we know, a couple rules about this base. It cannot be negative or 0. Our base, exponential bases, must always be positive, but it cannot be the number 1. Why, Mr. M? Because if our exponential base was the number 1, 1 to any power is always going to equal 1. So it wouldn't matter what we plugged in for x. B to the 1 would always be whatever b is. And what we would get is a times b, which is a number, plus k, which is a number. If our exponential base was 1, we would get y equals a number, which is a horizontal line and does not get curvy like either one of these. So that is why the base must not be 1. So it could be any positive number except for 1. Cool with that idea? Cool, lots of heads are shaking. So what determines the shape then? Well, if your exponential base is any number bigger than 1, then this is you multiplying by a number that's bigger than 1 over and over and over again. So let's just say I made you multiply by 1.5 times 1.5 times 1.5 times 1.5. These numbers are getting bigger and bigger and bigger and bigger and will skyrocket. If your exponential base is a number larger than 1, you're looking at something that is growth. Your base can't be 1, but your base has to be positive. I've already said numbers bigger than 1. Then this is how you get things, this is what you get from things that are between 0 and 1. So if your exponential base is a number like 3/4, I said let's take all the money that we have, now take 3/4 of it, and then 3/4 of it, and then 3/4 of it, and then 3/4 of it. These numbers should be getting smaller every single time we multiply by 3 over 4, and that is why we're decaying. Now I mentioned earlier that both of these graphs have a horizontal asymptote. Why? Because the exponential base must be a positive number. And you could raise a positive number to any power you want, and your result will always be positive. You know what it'll never be? 0. So because the base is a positive number, we can raise it to any power we want, and we will never get the value of 0 from that expression. And that is why they both approach 0, but never actually get there. Comfortable with that idea? Awesome. The base can't be 1. It can be between 0 and 1, yes, which is going to result in this. Like, let's say it's a 1/2. If I said take $100, now cut it in half, now cut it in half, now cut it in half. So every time we cut it in half, it's going to get smaller and smaller and smaller and smaller. It's going to crash towards 0, but never technically equal 0, because you could always divide a number by 2. We say that this function is always increasing, because everything is read from left to right. And because of that, we say this function is always decreasing, because everything is read from left to right. End behavior then, for both of these, is going to approach 0 on one side, infinity on the other. Now, if we reflect it, obviously it's going to approach negative infinity as it goes towards one of the two directions. There was one more thing I want to say. Oh, because both of these have a horizontal asymptote at y equals 0, and because all transformation affect all functions the same way, shifting a graph up and down will also shift its horizontal asymptote up and down. That's really important. So right there, that plus k is always going to represent your horizontal asymptote. Y equals k will always be your horizontal asymptote. That should be the very first thing you find when you're attempting to graph an exponential function. Its horizontal asymptote. After that, there are 2 more structures we need. So that's a total of 3 structures. The first one, horizontal asymptote. The other 2 are coordinates. There are 2 very specific coordinates that I want you to always find. Can you find more? Yes. Do you have to find the 2 that I suggest? No. But I'm suggesting the 2 easiest ones to find, and I'm setting you up for success for later material when we have to graph logarithms, because that's actually the next material. So I'm setting you up for success here. There are 2 exponents that are extremely easy to work with. Anybody want to take a stab at what the 2 easiest exponents are to work with? 1 and 0. They're nice and small. So let's always be figuring out what makes our exponents equal 0 and what makes our exponents equal 1. If we can track down these three things, we could sketch any exponential graph. Track down your horizontal asymptote, figure out what x makes your exponent equal 0 and evaluate, figure out what x makes your exponent equal 1 and evaluate. Sketch your graph and you're ready to rock and roll. So the things that I'm quote-unquote skipping because we've pre-learned them in 2 other courses, transformational knowledge, what is it really good? That's not even transformational. Transformational knowledge, what is it really good for? Multiple choice questions. That's what it's really good for. If you have a knowledge of transformations, then you'll be able to get rid of bad answers up front and then focus on what's really going to be important. So again, I'm not going to go through it, I'm just going to review it. Subtracting a 1 from your x's, this is an inside change because the structure that I'm talking about is our exponent. X changes are always opposite. So this is shift right 1 unit. This is a horizontal reflection. That means left and right. You must have moved across the y-axis. This is reflect over y-axis. And this is just vertical stretch factor 3. Again, just reviewing those things because it's not necessary for you to be able to list that. In fact, I'm going to edit the homework assignment to make sure that I remove those things. Okay? I just want to make sure that we at least say it. And what's that? Oh, she wasn't talking to me. And the last bit of quote-unquote information before we go to practicing is a very special exponential base. The exponential base e, also known as the natural base e. Why the letter e? 2 reasons. 1, the mathematician that discovered this number, notice how I said discovered, not created, discovered this number is Leonhard Euler. His last name starts with an E, E-U-L-E-R, Euler. Therefore, it's known as Euler's number. Also the letter E, because we need a symbol for this number. This number is irrational, like pi. No pattern, never stops. Because it has no pattern and never stops, the best thing we could do is give it a symbol. It's approximately equal to 2.718, not 2. That is a typo. 2.718. There's a 2 after the 8. You don't even need to really know that because you're going to have to work with your calculator when we talk about the natural base e. Now our authors, again, have written it in what I would say requires a little bit more information. And unfortunately, because they probably hate me, they have used the letter K here. I don't like it. I would rather use R. And the reason why I would rather use R is because you've seen it with an R before in Algebra 2. The PERT formula. This is continuous growth and decay for word problems, which we will get to, which are earlier you asked me what happened to section 3.2. It's word problems. I like to lump all my word problems at the end after I've done all of the exponential and logarithmic, let's say algebra and graphing. Then we'll do the word problems later. So it's not wrong to use a K. I'm just going to use an R for now because I want to write it like this. And then I'm going to do one very specific important thing. Yes, I stuck that parenthesis between the R and the X. The reason why I did that is because I want you to see that I could have written it like this. Where that E to the R, our author said K, is our exponential base. You see, E is a positive number. So we raise E to powers just like we do any other number. And anytime you raise a positive number to a power, you're always going to get a positive result. So this E to the K, E to the R, could have been written as a b. I would just have to grab a calculator and evaluate it. Let's say that that r was a 2. I don't know what e squared is. I would grab a calculator and I could have figured it out, and I could have written it like this. I'm not going to ever make you do that when we're graphing. But I want you to understand that because it could have been written that way, it's going to behave by the exact same rules. The only thing that you really need to know is what makes it growth or decay. If r, or k, whatever you want to call it, is a positive number, you're raising 2 and change to a positive number, your number is going to get larger. So if r, or k, whatever you want to call it, is positive, this is growth. Which means if r, or k, whatever you want to call it, is negative, you're going to get 1 over e to the whatever letter, which is now going to evaluate to a number between 0 and 1, which is why you're going to get decay. So if this right above the e is positive, growth. If this number right above the e is negative, decay. Other than that, horizontal asymptote stays the same. Sketching our graphs, we're going to find the 2 other structures. What makes the exponent equal 0? Because that's really easy, because e to the 0 is 1, just like everything to the 0 is 1. And we'll grab a calculator and we'll figure out what makes the exponent equal 1. It won't be any different other than we'll have to touch a calculator. Okay? Don't panic. I got you back. Again, these are just transformations, whatever. Horizontal shrink, factor 1/2, because anything that happens to the x is the opposite of what it looks like. Here's that horizontal reflection again, so reflecting left, right, that's reflection over the y-axis. Vertical stretch, factor 3, whatever. I really care. Could you, in a pinch, graph or say, yes, that's the equation that matches a graph? Because that is the real skills that are on my test. I'll go ahead and tell you. All the graphing questions on the test are multiple choice. It goes, here's an equation. Which one is the graph? It's multiple choice. The other graphing style questions go, here's a graph. What is its equation? Multiple choice. And in the multiple choice questions for what's the equation, they all have the same base. So I'm not even trying to be tricky. I'm not going to make you solve for an exponential base. You could, but I'm not going to make you. I'm literally asking, can you see where the horizontal asymptote is? Can you see a couple pretty points and make it match up? And if you can pull those things off, you're going to be set. All right? Okay. Let's get going on this one. Yes, it's got some transformations. If you understood the transformations, you could eliminate some bad answers right off the bat. Specifically, that negative sign on the front. If you know what that does, awesome, because you're eliminating bad answers immediately. This negative sign on the front is a vertical reflection. This is reflecting over the x-axis. This turns the graph upside down. So if that wasn't there, you'd have a growth function which goes up and to the right. But because it's there, it doesn't go up and to the right, it goes right. As it goes right, it goes down. So this graph will look like this. Just knowing that is going to eliminate bad answers. And the other thing, you should be able to find that horizontal line just by looking at the equation, because these are based on transformations. If you could pull that off, you probably are down to two answers left, maybe 3 at the most. And now we're just looking for pretty points. You don't know any of that stuff I just said? No big deal. I got your back. The one thing you must be able to do, though, is identify that. Because whatever number has been added or subtracted to the exponential, this would be the exponential, is always going to represent our horizontal asymptote. Y equals 3, horizontal asymptote. Might as well throw that on your graph. In our last chapter, we talked about how horizontal asymptotes are goals, and they tell you what's going on at the infinities, and they don't tell you anything about what's going on at the zeros. So because of that, some rational functions will cross their own horizontal asymptotes. Exponentials can't. It's not possible. The reason why is because this exponential thing, the closest value it's going to attempt to get to is 0. It'll never get there. It'll attempt to get there. And then we'll always be adding 3 to it. So the value of this function is going to forever get closer and closer and closer to 3, but it'll never actually get there, ever. We have a horizontal asymptote. Ready to rock and roll? We need to find the 2 structures that I talked about. 1, what makes exponent equal 0? Because that's easy. 2, what makes exponent equal 1? Again, because it's easy. Could I get more points? What makes exponent equal 2? What makes exponent equal 3? Sure, I could. It's just that exponentials grow really fast. So you'll fall off the grid rather quickly. It's just not necessary. Let's figure out what makes our exponent equal 0. So you take your exponent, whatever it is, you set it equal to 0, and you get x by itself. You're just going to subtract 1 from both sides. What we need to do is know what y value goes with that. And once we do, we have our first coordinate. So everywhere that I have an x, I'm going to put a -1. I almost forgot to put it there. Time to evaluate. That's easy, Mr. M. Everything to 0 is 1. 1 plus 3. Y is 4, right? No. Why? Oh. Oh, how about that? Yeah, if I said this was 1 and 1 plus 3 is 4, that would put me above this horizontal asymptote, and our knowledge of transformations tells us it goes down. So what went wrong? There it is. The order of operations says exponents first. That means that this negative sign is treated as a -1 times 2 to the 0. Those parentheses aren't there, but they're implied. So this is actually -1 plus 3, which is 2, which is below that horizontal asymptote. So we have a pretty point at -1 comma 2. The other thing we need to figure out is what makes the exponent equal 1. Again, I'm only choosing 0 and 1 because they're nice small numbers. They're going to keep me close to the horizontal asymptote. I don't have to worry about falling off the grid. So we take our exponent, set it equal to 1, and solve for x. You subtract 1 from both sides. You're going to get x equals 0. And then evaluate. Everywhere you had an x, you're going to put a 0. Once again, we should be doing exponents first, but we'll get away with it this time if we forget, because -2 to the first quantity is -2, and 2 to the first times -1 is still -2. But for good mathematics and good notes, because, you know, one of these days I'm going to monetize these videos and those will be my walking papers, what? We're going to get -2 plus 3 equals 1. So 0, 1, which is right here. Could I find more points? Sure. I can figure out what makes the exponent equal 2. I can figure out what makes the exponent equal 3, so on and so forth. But I don't need to. Because as long as you have the general knowledge of what the curve would look like, and you could see 2 points it's going to go through, you're pretty much set. Get infinitely close to this line without adding any extra wiggles to your graph. Make sure you go through these 2 points, and if you have knowledge of transformations, it'll look like that. Something like that. Now, I don't know exactly where it's going to go afterwards. I could throw in x equals 1 if I wanted to. I don't need to. It's just, that's good enough. That's good enough. I'm sorry? Didn't we what? No, we did x equals -1 and x equals 0. You're thinking we just did what made the exponent equal 1. If we throw in x equals 1, we'll get -2 squared, so -4. -4 plus 3 is -1. So 1 comma -1. Oh, I almost hit an actual point. Again, not really important. Questions about that before we move on to another example? No? All right. So again, were transformations necessary? No. Were they helpful? Sure. By the way, when we were doing quadratics, I've said the words, what makes the inside equal 0, comma, the number to the far right. That's going to be the vertex anytime you're in vertex form. I would like for you to notice what makes the inside equal 0, -1, comma, the number to the far right, comma 3, is not a point on this. It's 2 different structures. What makes the inside equal 0 did happen. The number to the far right did happen, but they were 2 completely different things. They were still really useful information, though. Does that make sense? What makes the inside equal 0 and the number to the far right are always really useful pieces of information when you're graphing functions. You gonna make it? Slowly coughing to death back there. Okay. This time the exponential base is 3. My exponent is written in a strange order. Do we need to have knowledge of transformations to do this? No. But is it helpful? Absolutely. You see, the parent exponential growth function goes up as it goes to the right. But that is what happens when x is positive. In the equation, I should say. Whereas this one, x is negative in the equation. A knowledge of transformations then tells us that this is a horizontal reflection. This thing is not going to go up as it goes to the right. It's going to go down as it goes to the right. But let's just say we completely forgot that, had no clue. That's okay. As long as you can track down your horizontal asymptote and the 2 exponent structures, you're going to be just fine. Horizontal asymptote at y equals -4. And then our 2 structures. First, let's figure out what makes that exponent equal 0. We take our exponent, whatever it is, and set it equal to 0. 2 minus x is 0. You can either do the algebra or you can use a little bit of common sense. 2 minus what is 0? 2. We are going to have a pretty point at 2 comma something. Time to evaluate. Everywhere there's an x, we're going to throw a 2. No trickery this time. It does say 3 to the 0, which is 1. We have a pretty point then at 2 comma -3. The next structure is what makes that exponent equal 1. Take your exponent, whatever it is, set it equal to 1. You could do the algebra, or you could use a little bit of common sense. 2 minus a number is 1. Hopefully it's obvious that that number is x equals 1. And then carefully evaluate again. Everywhere there's an x, you put a 1. And 3 to the 4th is, 3 to the 4th, 3 to the 1st is 3. And 3 minus 4 is negative 1. Our second structure, second pretty point is 1 comma negative 1. So your graph needs to be a curve. It needs to get infinitely close to the red dotted line. It needs to go through those 2 green dots. Don't introduce any extra wiggles to this thing. I think it makes it pretty obvious what's going on. Let's see, how do I do this so that it looks good? Could we get more points? Absolutely, we could. We could throw in x equals 0 and get y equals 5. I was close. I missed it a little bit, but whatever. Before we go on to the last example, I'd like for you to notice that the second example that we just did, the graph is much steeper than the first. Anybody think they know why? Bless you. Why it's steeper? Hold on, what? Not negative 2, but 2. Yeah, because the negative is its own thing. Yeah, literally, the exponential base changing is what changed the steepness of the graph. This exponential base of 2 is a graph that is not as steep as this graph that has exponential base 3. So if I said exponential base 4, hopefully you would expect a graph that was even steeper. If I said exponential base 1/2, hopefully you would expect a graph that is not as steep. So on and so forth. And lastly, by the way, what that implies is changing the exponential base is a form of vertical stretching and shrinking. It is. We'll see how after we've done some logarithms. But last example for today, sketching the graph of an exponential that is natural base e. It's helpful if you know transformations, not necessary. If you can find the horizontal asymptote and you can find the 2 numbers I want you to find for x, you're in good shape. Cool. Horizontal asymptote in the books. Let's figure out what makes this exponent equal 0. We take what our exponent is, whatever it is, and set it equal to 0. What is x? I hope it's obvious that it's 0. I only put a set of parentheses there so it doesn't look like I wrote negative 20. Just showing that it's multiplication here. And negative 2 times 0 is 0. Everything to the 0 power, well, any number that's positive to the 0 power is 1. So 0 comma negative 3 is on our graph. One more coordinate and we're set. I wrote 0 again. Oops. You divide both sides by -2. And it gives you x equals -1/2. Oh no! A fraction! A decimal! Eek! No big deal. It's right there. No sweat. We know where -1/2 is. Let's get plugged in. It is going to be a yucky number, yes. It's irrational. It gives me e to the first power. Now, I don't know exactly what e minus 4 is. I do know that e is 2.718-ish. So I know that this is going to be a negative result. I know that I'm going to be here at x and then a negative result, which means I know my graph does this. I'm going to grab a calculator, make sure it makes it onto the video to show you how to do this. So we'll start with the best calculator on the planet. That's not true. They get even better. Graphing calculator. Yes, you should be using it to get good with it, but you should also be able to use other calculators as well, because you will not be allowed to use this graphing calculator on my test because it'll do the questions for you. But here's how we operate it. E is right there in blue writing on my calculator. Blue writing requires the blue button. Second, ln. You'll notice that the calculator is waiting for an exponent. I said that it's the first power. 1, enter. Then just -4. -1.3-ish. Can we say about -1.3? Comfortable with that? Okay. Before I plot this thing, I would like to show you how to do that on this pretty decent calculator. You'll notice that, once again, E is going to require you to press another button. It's a white command, so I have to press the white button. Second, ln, and this calculator is also waiting on an exponent. If I hit enter, it goes, man, you dumb. You go, okay, I forgot something. Go back, first power, close it up, hit enter. And the calculator that we should all know and hate, this one. You cannot type E first. This calculator makes you type the X first. First power, second, there you go. Oh no, the bell, eek! That's like, what, here? There you go, good enough. That's a steep one. All right, buddy, I'll see y'all tomorrow.